The first type of chemical bond we'll talk about are ionic bonds. Now, ionic bonds are chemical bonds that are based on electrostatic attraction. In other words, you have two atoms that have an electrostatic charge, and charges of opposite polarity, in other words, a positive and negative charge, will attract each other. Generally, when you have an ionic bond, it forms a crystalline type of structure. Simple example, let's take a look at sodium chloride, also known as table salt. Now, you look at sodium. Sodium is in the first column of the periodic table, which means it has one valence electron, which you see here. Chlorine, on the other hand, is in the second to right column of the periodic table, which means it has seven valence electrons. Now remember that the goal is for each of them to have 8. The easiest way for this to happen is for sodium to lose that extra electron, and by losing that extra electron, it now goes down to the next electron shell, which will be completely full. And then chlorine would be best to accept that extra electron. So as a result, sodium becomes negatively charged or positively charged, because there's one less electron, and so one more proton than electrons. Chlorine then becomes negatively charged because it has one extra electron. So now that you have a positively charged sodium ion and a negatively charged chlorine ion, they are attracted to each other and start to pattern themselves in a sort of crystalline shape, a structured pattern. And this is each shape depends on the specific elements that are attracted to each other. But in this example for sodium chloride, it is a very cubic shape. And so if you were to put table salt under a microscope, this is often what you would see, a very cubic form of structure. Now, when you have an ionic reaction, there's often energy released in the process, whether in combining the two elements or splitting the compound. One way or another, energy is released. It's easier to look at this if we divide the formula into half reactions. So for instance, we have sodium with one extra electron. We want to lose that electron, so you add energy to it and you separate them. You get positive sodium ion and an electron. Then you take chlorine and you introduce that extra electron, and when the electron drops into the chlorine, then you release energy. Well, the amount of energy in steps 1 and 2 are not the same. In fact, for this reaction, the amount of energy released in step 2 is going to be larger than the amount of energy absorbed in step 1. As a result, you're going to have a net amount of energy released at the end of the reaction. So if you were to have sodium and chlorine together, put them together, you would actually heat up the area around it because of the reaction. Do remember your electron transfer rules. We're going to see this a couple of times today in the rest of this lecture. The transfer rules is that the number of electrons lost or gained have to bring that element to the closest octet. So sodium lost an electron to form a new octet. Chlorine gained an electron to form an octet. And another very important rule with electron transfer is that the number of electrons gained has to equal the number of electrons lost. When you look at an ionic compound, first of all, an ionic compound is always characterized by ionic bonds, these electrostatic attractions. it always forms kind of these white crystalline solids, crystal shape, and with table salt, sodium chloride, we saw that that was a very cubic solid. It also turns out to be soluble in water. Now, if you look at the two elements in an ionic compound, you're going to have one from the first or second columns 1A and 2A of the periodic table. Those will always lose electrons to become positive ions. And then the other element in the compound will be in either column 6 or 7, or 6A or 7A from the periodic table. Those will always gain electrons and become negative ions. The formula for each of these compounds is made by listing the elements of the compound in their actual proportions. So, for example, in this example, you have a calcium atom and a fluorine atom. Well, calcium has 2 extra electrons, so it's going to have to get rid of 2 electrons to create the octet. But fluorine only has room for 1. So calcium becomes a +2 ion, whereas fluorine is just a -1 ion. So in order to balance all those charges, you're going to need 2 fluorine atoms to make this to make the electrostatic balance. And so this is the proportion that we need. The amount of proportions of one atom to the other is decided by the electrons gained versus the electrons lost. When we name ions, well, let's get to naming in just a second. First of all, when we write out the formulas, we always follow this rule. First of all, write the symbol for the positive ion first, and then the negative ion second. So in this example, we have calcium, which becomes a +2 ion, and chlorine, which becomes a -1 ion. So we would start by writing first the metal, and second the non-metal. And then you assign subscripts to assure the compound is electrically neutral. In other words, calcium has +2, chlorine has -1, so you're going to need 2 chlorine atoms to balance the calcium's 2 charges. So if you need 2 calcium ions, you get that, you use the subscript 2 to indicate how many you have. This element is called calcium chloride. Now let's name a couple of ionic compounds. First of all, as we just said, we named the metal first and the non-metal second. Now, some elements can have different numbers, different possible charges. For instance, iron. Iron is element Fe. In order for iron to create an ionic compound, it can actually have 2 possible scenarios. Either it can lose 3 electrons, so it would have a charge of +3, or it can lose 2 electrons, +2. Now, historically, the way we would name this is this would be iron 3, and this would be iron 2. But in the naming sequence, we would use the suffix ic if it's higher than 2, us for 2 or lower. So this would be ferric, and this would be ferrous. So let's combine it with oxygen. Remember that oxygen can lose 2, so it has a charge of -2. If we have iron 2, or the ferrous atom, then it has a charge of +2, oxygen has a charge of -2, just have 1 atom of each, combine them together, and that's balanced. you have ferrous oxide. Recall that the IDE at the end is the suffix on the nonmetal that we use when there are only two elements involved. But if we use the iron 3 atom, it has a charge of 3, but oxygen has a charge of -2. So in order to get this to balance, let's take two ferric atoms. That would give us two ferric atoms of charge 3 each would give us a total charge of +6. And to do that, we would need a total charge of -6 from the oxygen, which means we need 3 oxygen atoms. This would be what we call ferric oxide, because of course we're dealing with iron 3, which has higher than 2, has a charge of higher than 2. Now that's a historical naming sequence. This is mostly used for the metals in the center of the periodic table. When we're dealing with irons, with most metals, we're dealing with the first couple columns of the periodic table. So you can have a charge of either +1 or +2. In the case of aluminum, you could have a charge of +3. And then the last couple columns, you could have a charge of -1 or -2. So the more modern approach to naming ionic bonds is to name the metal and then the nonmetal. So, for instance, sodium chloride, just name the metal, and then name the second metal, the nonmetal, which would be sodium, and then chlorine. But instead of the INE, we replace that with IDE, sodium chloride. And that's the typical naming sequence for ionic compounds.